This is by Wang, Kui, Kao, Zygmunt, Volos, Mutlu, Lu, Fong, and Xu, right?
Yeah. Okay, hello everyone. Yeah, my name is Chen Wang. The title of my topic is Panthera, holistic memory management for big data processing over hybrid memories. Yeah, we use NVM to extend the main memory and does the calculation on the NVM. Okay, as we all know, lots of big data workloads such as Spark and Hadoop, they are written in major languages, and they require higher and higher memory capacity. And at the same time, we want to reduce the energy consumption of the servers. However, for the DRAM, it already accounts for up to 40% of the total energy consumption. And at the same time, the capacity density of DRAM is starting to hit the fundamental limit. Okay, for the non-volatile memory, it's an emerging better addressable memory technology. Compared to DRAM, the NVM has higher memory capacity density, lower price, and negligible background energy consumption. However, the performance of NVM is much worse than DRAM. It has increased memory access latency and reduced bandwidth. So, in order to utilize the good performance of DRAM and the low energy consumption of NVM, integrate DRAM and NVM into hybrid memory is a promising way to satisfy the big data applications requirements. Because the performance of NVM is much worse, so the key challenge to use this new memory architecture is how to place data appropriately so that we can reduce the energy consumption and at a minimum time cost. Okay, next I will introduce the opportunities and the challenges of the hybrid memory management for big data applications. Okay, a common approach to manage the hybrid memory in the manage the runtime level. The first step is to divide the Java heap into DRAM and NVM areas. And then we profile the access frequency of the objects and migrate the frequently accessed objects from NVM to DRAM. For example, if the purpose is to optimize the durability of the NVM, for example, the write rationing does, it migrates the write-intensive objects from NVM to DRAM. Yeah, this is because the write endurance of NVM is much worse than DRAM. However, this approach is not suitable for big data applications because big data applications, it has billions of objects. If we do profiling, we do online profiling at object granularity, it will cause significant performance overhead. Okay. For the big data systems, such as Spark, they all have application level memory subsystems, which can perform memory management at coarse granularity. Yeah, for example, Spark manages data and does computation at RDD granularity. RDD is a distributed data collection. And we all know that different RDD has different and clear access patterns. For example, some RDD are only used for fault tolerance, and some RDD are frequently reused for computation. And because the objects within one RDD all have the same access pattern and lifetime, so it's a good opportunity to use the characteristics of the RDD to divide the objects into coarse-grained. And this method can save lots of online profiling overhead. However, the problem is that for the runtime, it cannot see the semantics of RDD, except for a bunch of low-level Java objects. Therefore, we need to find a way to bridge the gap between the high-level data structure and the low-level Java objects. Okay, next I will introduce our solution, Panthera. Based on OpenJDK, we developed Panthera, a holistic memory management system for big data systems running in the managed runtime. The Panthera manages the hybrid memory in a holistic way. First, it gets the physical memory, the physical DRAM and NVM memory from OS, and maps the Java heaps to the physical DRAM and NVM. Second, Panthera uses application-level semantics to divide the objects into coarse-grained categories. And for the data profiling mechanism, Panthera provides both the static inference and the coarse-grained dynamic analysis. As we have said, for the data-intensive applications, they manage their data in a coarse-grained manner. And the data access patterns and the lifetime are usually statically observed. For example, the picture shows the code segment of the Spark page rank. Okay, we can see that for the RDD links, which is defined beyond the loop and is frequently reused within the loop, so it should be marked with DRAM tag by the Panthera. And the RDD contributes, which is defined within the loop. And for each iteration, it will generate new data for the RDD contributes. Sometimes, if the programmers want to persist the RDD contributes for fault tolerance, so we need to mark the RDD contributes for NVM tag. Okay, finally, Panthera by using the static analysis to infer the access frequency of the RDDs and mark the RDDs with different tags based on their access frequency. However, the problem is that we have said that each RDD consists of a bunch of low-level Java objects, and all the objects within one RDD should be placed into DRAM or NVM according to the RDD tags. And it's not practical to use the static analysis to find and mark all the RDDs within, find and mark all the objects within one RDD. But the garbage collection brings the opportunity to bridge the gaps between the high-level data structure and the low-level Java objects. Okay, because for each garbage collection, the JC will trace all the level objects from the root. Okay, something like this. So for Panthera, we only need to mark one RDD root object, and then this tag will be propagated to all the reachable objects from this RDD root object. So by using the static analysis and the text propagation, the mechanism, for the static analysis, we incur almost zero online profiling overhead. Also, the static analysis is already good enough for the big data applications. Panthera also provides a low overhead dynamic profiling mechanism. That's in case that the static analysis isn't that accurate. For the dynamic profiling, Panthera monitors the number of the function invocations, on the RDD root object, and write this value into the object header. So during each major JC, it will check the value of the header, and it will change the tag according to the value. And these objects, when the text is changed, the JC will migrate these objects to DRAM or NVM according to their new text. For the data placement in Panthera, it's done based on the DRAM and NVM tags. First, all the objects are allocated according to their tags, and whenever their tags are changed, so JC will migrate the objects according to their new tags. After getting the application level semantics, Panthera has done some runtime level optimizations. For example, the eager promotion of RDD objects. We can see that if the RDD, the tagged RDD, they belong to the persistent RDD. Oh, sorry, the tagged objects, they belong to the persistent RDD. And they all have a very long lifetime. So Panthera can promote these objects to the old generation directly. Without waiting for that, they survive several minor GC. So it can eliminate loss of useless memory access. Yeah, there are for the big data, big array alignment padding. Yeah, if you want to know more details, yeah, please read our papers for this. Next, I will introduce the evaluation. Because existing NVM simulator cannot support for the commercial runtime well, for example, the OpenJDK. So based on the NUMA architecture, we developed a hybrid memory emulator, which can support the big data applications. We fixed the application running on one CPU. And when it accesses the memory of another CPU, the Intel QPI, the quick path interconnect, will make the memory access latency much longer. And gets inspired by the paper of course, we use the thermal register to limit the bandwidth of the remote memory. So finally, compared to the DRAM, the emulated NVM has a 2.5 times longer latency and only have 1/3 DRAM bandwidth. The emulated parameters of the NVM are consistent with the NVM specs. For the experiment setup, the applications running on the DRAM only is used as the baseline. And we compare our work with Panthera with the unmanaged version. For the unmanaged version, its young generation is mapped on DRAM, like a restoration JC does. And its old generation is mapped on DRAM and NVM in an interleaving way, like the picture shows. The picture shows that the NVM and DRAM interleaving in the 1/3 DRAM ratio. And we use different DRAM ratios in our experiments. And the performance of the unmanaged version is at least as good as the restoration JC. Okay, this slide shows the overall results of the performance. All the results are normalized to the baseline DRAM only. The blue bars show the results of the unmanaged, and the orange bars show the results of the Panthera. We can see that under the configuration of 64 GB heap and 1/3 DRAM ratio, Panthera only has a 4% performance overhead, and at the same time, unmanaged version has a 21% performance overhead. Okay, this slide shows the overall results of the energy consumption. All the results are normalized to the DRAM only. And under the same configuration, 64 GB heap, 1/3 DRAM ratio, Panthera saves about 32 energy consumption. And we can get much more energy benefit with a larger memory size. For example, under 120 GB heap, the Panthera can save about 50% energy consumption. Okay, this slide shows the results of the JC performance under the same configuration. The gray bars shows the results of the DRAM only. Orange bars are Panthera, and the blue bars are managed version. Okay, we can see that for the unmanaged version, it has about 60% JC performance overhead. This is because the JC is highly paralleled and bound by the NVM latency and bandwidth heavily. In our experiments, the GC has about more than 20 threads. And Panthera eliminates both the NVM latency and the bandwidth bound by doing two things. First, it migrates the frequently accessed and long lifetime data from NVM to DRAM. Second, as I have said, we have done, after we get the application level semantics, we have done some runtime level optimizations. Finally, the Panthera only have 1% JC performance overhead. Okay, this slide shows the performance of the Mutator. Also, the Mutator is also highly paralleled because for the we run the Spark based Spark applications there. So the Mutator also highly paralleled, but the Mutator has done much more calculation than JC. So this is why the Mutator doesn't generate that high memory bandwidth. And after applying our optimization, the Panthera only has a 3% Mutator performance overhead. Okay, based on OpenJDK, we developed the Panthera, a holistic memory management system for hybrid memories. The Panthera is designed for big data applications, and it uses application-level semantics for coarse-grained data placement. And the Panthera can reduce the energy consumption significantly at a small time cost. Okay, that's all. Thank you.
Get the chance this time.
Okay.
So if you remove static analysis and just use the garbage collection to do all the work, and maybe ignore even RDDs, just use it as is, do you know if it will be a lot worse or approximately the same?
Or you mean apply our optimizations for the DC?
Right, you move it with the GC, but you don't start with static analysis to make it, initially better.
Oh, the question is, you mean our optimizations are applied to the GC, has nothing to do with NVM, right?
Right, you try to decide which is warm and which is colder,
yes,
right?
Yeah.
And you just let the GC decide according to the activity in the program, but don't use static analysis initially to determine what is an RDD. You know what will happen, or this is something?
Oh, okay, I understand. For the static analysis, we do the static analysis for the application, right? Yes, we use the static analysis we use static analysis to analyze the application and mark the RDD. We have provide some RDD persistent level, for example, hot or cold, something like this, to mark the RDD. And after this value will change the header bit and pass this information to the runtime.
Okay.
And for the JC, when you do JC, you need to check the object header first. For example, one bit for DRAM and two bits for NVM, something like this. After you check the bit, and the GC, you just propagate the tag, the bit, to other objects you referenced. Yeah, sometimes there's conflict, right? Some objects are referenced by the DRAM, and some objects are referenced by the NVM at the same time. And the DRAM has a higher priority. If an object is referenced both by the DRAM tag and NVM tag, the DRAM has the high priority. Yeah, I can understand sometimes we can mark more objects than the RDD. For example, RDD reference only 10 objects. Maybe we can mark 11 or 2 objects because some temporary objects belong to the RDD. And we move all the RDDs from NVM to move all the objects to the DRAM or NVM separately. Have they solved the question?
Thank you.
Okay, thank you.
Any more?
Okay. So if you so in the example you're showing, you've already allocated that object, and you say later that you want to persist it?
You mean the RDD contributes, right?
Pardon?
I mean, your question is about the RDD contributes.
So so you could mark only the object as persistent or unpersistent when it gets allocated.
Oh, yeah.
You're showing an example where you're saying persistent sometime later after allocation, right?
Oh, no. We only mark the persistent RDDs. For the unpersistent RDDs, most of the RDDs, their data objects are die in the young generation. Right. We don't need to handle this kind of RDD because we already map the young generation to the DRAM, right? Yeah, they will die very fast. So for our solution, we only mark the persistent RDD, and they can't change it. For example, You mean the processor and unprocessor, something like this?
So when you're marking, it looks like to me in the example,
Okay.
you mark the object sometime later after it gets allocated.
Oh, no.
So it,
Sorry, we mark before it's allocated.
that's my question. Thank you.
Okay, let's thank the speaker again.